Okay, so we are looking at some more things from section 2.5, zeros of polynomial functions continued. We are looking at Descartes' rule of signs. René Descartes, a French mathematician about 400 years ago, gets credit for this special rule to help you determine how many real zeros a polynomial will have. Descartes' rule of signs goes like this. It is let f of x be a polynomial with real coefficients and a not equal to 0. If you have, remember, we can talk about the polynomial function in general terms like this, where a sub n is the leading coefficient, all the a's are the coefficients, this would be a degree n, and so on. You're hopefully getting comfortable seeing this written out in general way like this. And the first rule, the first part of Descartes' rule says the number of positive real zeros of the function f is either equal to the number of sign changes in f of x, or it's going to be less than that number by an even integer. All right, so for example, if we have a polynomial function like f of x equaling negative 7x to the fifth plus 4x cubed minus 2, how many sign changes are there? Well, this coefficient was negative, and then it went to positive, so that would be one sign change. And then it goes from positive to negative, so that's a second sign change. Does that make sense? So how many positive real zeros could this function have? 2, or less than that by an even integer. So it's either 2 or it is what? 0. So our conclusion for this would be this has either 2 or 0. I don't want to write out 0. 2 or no positive real zeros. So what are we talking about? We're talking about how many places is that graph going to cross. If we're going to graph a polynomial function, how many places is it going to cross to the right of the y-axis, right? Because we're talking about positive real zeros. So it's either going to cross in 2 places, or it's not going to cross at all to the right of the y-axis. Does that make sense? Okay. What about what's happening to the left of the y-axis? What about those negative real zeros? Well, that's where the second part of Descartes' rule of signs comes in. The number of negative real zeros of the function f is either equal to the number of sign changes in f of negative x, or is going to be less than that number by an even integer. So if I stick with my original example from here, and I try and find f of negative x, you know that means I got to take out every x and replace it with the opposite of x, right? So I need negative 7 times opposite of x to the fifth plus 4 times negative x to the third minus 2. And we simplify this. What's negative x raised to the fifth? Is that going to be positive x to the fifth or negative x to the fifth? Negative. And I'm going to multiply that by a negative 7, so isn't that going to give me a positive 7x to the fifth? And then here, negative x to the third, or negative x quantity to the third, is that going to be positive x to the third or negative x to the third? Negative, because it's an odd quantity of negatives, and that's being multiplied by a positive 4, so isn't that going to give me a minus 4x to the third? And then we have minus 2. So how many sign changes were there here? It started out positive, and it went negative, so that's one sign change. Did it change again? No, it stayed negative. So there is only one sign change, so what conclusion could we say about this? All right, it's going to have 1 0 to the left, on the left side of the y-axis, 1 negative real zero. So there is guaranteed to be 1 negative real zero. All right, can you please type this function into your graphic calculator so we can test Descartes' rule of signs and see how we did? we are predicting either 2 or 0 positive real zeros. That means we think it's going to either cross twice on the right side of the y-axis or not at all. And we do believe it's going to cross exactly 1 time to the left of the y-axis, meaning 1 negative real zero. All right, and let's see. Brendan, you've got this graphed. What are we noticing? There's 1 negative real zero, and how many positive real zeros? None. All right, so Descartes' rule of signs seems to work with this. By the way, what degree was this polynomial function? 5th. So if it's degree 5, how many zeros should we have altogether? 5, right? And how many real zeros did we find? 1. So what about the other 4? They must be imaginary. And I just made this guy up. I mean, I just made this one up just now. All right, so let's continue here. All right, do you have this example on your gift? No? Do you have, is that the same one? Does that look like the same one? Because it is the same one. No, so you don't have any, or you do have something on your gift about Descartes' rule of signs? You do. All right, let me get that. Might be helpful to get that. Okay, yeah, you've got number, wow, number 5, but there's no number 4. Quality control, I don't know. Okay, so we're trying number 5 from your gift. It says use Descartes' rule of signs, 2x cubed minus 5x squared plus 12x minus 5. How many sign changes are there in this? Is it 3 sign changes? Going from positive to negative, negative to positive, and positive back to negative. So what is your conclusion that you would make here, Greg?
There are either 3 or 1 zeros the right of the y-axis.
Okay, so 3 or 1 positive real zeros, meaning the graph is going to cross the x-axis either 3 times or 1 time to the right of the y-axis. Okay, can you please find f of negative x to determine the quantity of negative real zeros? And what does this simplify down to, Nathan?
Negative 2x cubed minus 5x squared minus 12x minus 5.
So what's our conclusion, Anne?
There's 3, 0, negative real.
Okay, so we can say there are no negative real zeros. It's not going to cross the x-axis at all to the left of the y-axis. Can you test that? Graph this function, please. This is this function right here. Helpful if I auto-refreshed. Okay, Matthew Novak. You got this graphed? I just would like to see more of this graph. Can you zoom out? I know I don't usually say zoom out, but I usually say choose your window settings, et cetera, et cetera. But it just looks so straight. Anywho, yeah, call it what you will. It looks like it is just kind of there. Okay, so how many zeros do we have? How many real zeros do we have? One real zero. One positive real zero. Everybody agree? And no negative real zeros, just like we predicted with Descartes' rule of signs. And then what about imaginary zeros? There must be two, because this is a degree 3. We're guaranteed to have 3 zeros. We have one positive real zero, I should say. So we must have 2 imaginary zeros. Nathan?
For the first example that you did, you said there was either like 2 or 0 positive. Why in this one is there either 3 or 1?
Because the rule says, let's see where we're at. Because the rule says it's either going to be equal to the number of sign changes or less than that number by an even integer. So if there were 5 sign changes, you would either have 5 positive real zeros or 3 positive real zeros or 1 positive real zero. If there were 6 sign changes, you would either have 6 positive real zeros, 4 or 2 or none. Why do we subtract off 2? Why is it 2 every time that we subtract off? Why are we subtracting off even quantities of zeros? Because if we don't have 3, we're down to 1, so what does that mean about the other 2? Let me ask this again, because it's a good question. So let's say, in this example, we have either 2 or no positive real zeros, right? And it turned out to be none. Is that correct for that graph? So what happened to the other 2? We said it was a degree 5, right? So we know we're guaranteed to have 5 zeros altogether. So what happened to the 2 zeros I was down to? It was either 2 or none. But if we're down by 2, those 2 must be picked up by what kind of zeros? Imaginary. So why do the imaginary ones come in pairs? They do, because if you have 0 a plus bi, then you're guaranteed to have the 0 a minus bi. Complex zeros, they come in conjugate pairs. All right, does that make sense? Okay. All right, let's move on to the upper bound and lower bound test. All right. Okay, the upper bound and lower bound test. Again, remember this obviously predates graphing calculators. This would be like 200 years ago, 400 years ago. They needed some tests to help them graph polynomial functions. They could not reach for their TI Inspire. So the upper bound and lower bound test goes like this. This is a way of saying, if I pick a number like 10, am I guaranteed that there's going to be no zeros to the right of that number? Is 10 an upper bound for all my zeros? Does that make sense? So I won't have to go looking. It's not going to strangely come back up and go through the x-axis again somewhere to the right of 10. Okay, so it says let f of x be a polynomial function with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic division. If the c value is greater than 0 and each number in the last row of your synthetic division process is either positive or 0, then c is going to be an upper bound for the real zeros of function f. There will be no real zeros higher than c. All right. The second part is, what if your c value is less than 0? If c is less than 0 and the numbers in the last row are alternately positive and negative, and 0 entries can count as either positive or negative, then c is going to be a lower bound for the real zeros of the function. And that means there will be no real zeros to the left of c. So let's do this. Do you have an example on the gift? Oh, you know what? Let's let's look at one of your homework problems from the book. Number 87. Let's take a look at 87. Number 87, I'm on page 181. And you are asked in that problem to use synthetic division to verify the upper and lower bounds of the real zeros of the function. And it is x to the fourth minus 4x cubed. And it is what number is that? Plus 15. Everybody okay with this? So what are we doing? We are testing for part A. Is 4 going to be an upper bound? So how do we do that? We put 4 in the box, and we do synthetic division. 1, negative 4, I don't have an x squared or an x to the first, so I need 2 zeros, and then 15. I do the synthetic division process, bring down the 1, multiply, I get 4, add, I get 0, multiply 0, add 0, multiply 0, add 0, multiply 0, add 15. So, going back to our upper bound test, if c is greater than 0, and it is, it's a positive 4, and each number in the last row is either positive or 0. So out of these numbers here, hello, out of these numbers here, are they all either positive or 0? Yes, then that means that C, meaning 4, is going to be an upper bound for the zeros. Now, I have no idea. That's not what I want to do. So I have no idea what this graph is going to look like, but I know that the graph may zip around a bunch of times. Who knows? But I know that once I get to 4 on my x-axis, there will be no more zipping through the x-axis to the right of that, because 4 is an upper bound for the zeros. Does that make sense? There will be no zeros to the right of 4. Everybody agree? Okay, and can we use that same function and verify that negative 1 is a lower bound? So I'm going to put negative 1 in the box, and I'm still using, what was it? I'm still using 1, negative 4, 0, 0, 15. Does this look right? And I'm doing synthetic division with this. Bring down the 1, multiply, that's negative 1, add, that's negative 5, positive 5, adding, I get 5, that's a negative 5, adding, that's a negative 5, multiply, I get 5, add, I get 20. Does this look okay? What do we notice about these numbers here in this last row?
Negative.
What are they doing as we go from left to right? They're alternating. They're going positive, negative, right? Positive, negative, positive, negative, positive. That guarantees that, I go back to my graph, that this graph might be zipping along, might be zipping along to the left of the y-axis, but there will be no crossing the y-axis, no crossing the x-axis again to the left of negative 1, because it's a lower bound. Does that make sense? Let's graph this one to verify. Can we? Type this one into your calculator, please. All right, let's see. And you got this one in there? Okay, so what are we noticing from our graph? I see 1, 2, 3, 4. Here's 4 right here. And we said that 4 was going to be an upper bound. So we should not have this graph crossing the x-axis anymore to the right of 4. Does that make sense? And we can see that negative 1 here is a lower bound. In other words, there's going to be no crossing the x-axis to the left of negative 1. Are we okay? Now, we could do that same test for an upper bound. Let's try 3. I think it should fail, right? It should not work because it is crossing to the right of 3. So let's try 3. So what were the numbers again?
1, -4, 0, 0.
All right, so if we try it with 3, we should see that it doesn't work for 3. 3 is not going to be an upper bound, I don't think. So I get 3 at, sure, right there. So I get -3, add, I get -3 here, multiply, I get -9, -9, -27, -12. Right? So these are not all positive or 0 here. Does that make sense? So now I know that 3 is not an upper bound for the zeros, right? Because here 3, it is going to cross, the graph is going to cross to the x-axis to the right of 3. Are we okay with this? Okay, that is the upper bound and the lower bound test in action. So I would like to take a look at the 3 more hints that are on your gift there. 3 more hints. Whoops, there they are. For finding zeros. Always look for common factors first. Try to get down to a quadratic factor, and then you can use quadratic formula to find the remaining zeros. And the other important point is that complex zeros and irrational zeros come in conjugate pairs. All right? Complex zeros and irrational zeros come in conjugate pairs. So okay. All right, so with that in mind, I would like us to try number 7, which on the gift, which is find all the zeros of the function and write the polynomial as a product of linear factors. So that is not that one or that one. Let's put right here. Number 7 from the gift. F of x equals x cubed plus 9x squared plus 27x plus 35. All right. Let's kind of practice using all of our techniques that we've been learning in this section. So let's start off by listing possible rational zeros. That's the P over Q values. Okay, so we're going to find the P over Q values as possible rational zeros. Matthew.
Do you want me to start this meeting?
Sure.
35, 5, 1, 7.
That's it? Okay. So those are my P values. The Q values are going to be the factors of my leading coefficient, but that's just 1, so I just get plus or minus 1. So my list is going to be plus or minus 1, plus or minus 5, plus or minus 7, plus or minus 35. Okay? We could determine right now if there's any real zeros, let's say to the right of 4, right, for example, to know whether I can rule out any of the like the positive 5, positive 7, and positive 35. Does that make sense? If we do the upper bound test, I can plug in 4, for example, and 1, 9, 27, 35. Might need some help with the calculator. Bring down the 1, multiply, I get 4, add, I get 13, multiply, I get, is that 52? Add, I'm getting 79. Multiplying, I'm getting what? 316. Adding, and I'm getting 351. Does that look right? So what can we determine from this? Four is an upper bound, so what does that tell me about my choices here? I can rule out positive 5, I can rule out positive 7, I can rule out positive 35. Does that make sense? I could do the same thing for negative, but for right now, let's just graph this to get a head start. So go ahead and graph x cubed plus 9x squared plus 27x plus 35. Do we have this graphed? Lily, is that what it looks like? Okay, so it looks to me like, sure, nothing's happening to the right of 4, nothing's happening at all on the positive side, right? That's the other thing we didn't do. We didn't check for the number of, we didn't use Descartes' rule of signs yet, did we? To find out how many real, positive real zeros or how many negative real zeros. Let's pause for a moment and do that. So let me go back here. If we use Descartes' rule of signs on this function, I am going to look for sign changes, right, in the original. It goes positive, positive, how many sign changes do I have in the original? None. So I'm guaranteed, that means I didn't even have to look for this. I didn't even have to do this. I could have said, oh, it's not going to be any positive real zeros, so I can eliminate all those. If I try f of negative x to find the possible number of negative real zeros, this is going to be a negative x quantity cubed plus 9 times negative x quantity squared plus 27 times negative x plus 35, right? This is going to be negative x cubed. This is going to be a positive x squared. This is a plus 9x squared. Does that look right? Minus 27x plus 35. How many sign changes do I have? First of all, did I do this right? Does that look okay? How many sign changes do I have? 3. There's 1, there's 2, so 3 sign changes. So what is the conclusion that we can make? 3 or 1. There's going to be 3 or 1 negative real zero. Right? Does that mean that one of these negative numbers has to work? Negative 1, negative 5, negative 7, negative 35? I'm being skeptical. Why are you being skeptical? You look like you're skeptical, Brendan.
Because can occur between that and the 0 doesn't have to be an integer.
Doesn't have to be an integer. Doesn't have to be rational. This is just saying you're guaranteed 3 or 1 real zeros, right? They don't have to be irrational. I mean, they don't have to be rational.
I'm a little confused about the upper and lower bounds.
Yeah.
How do you know that there's not going to be any numbers after it that could be a bound?
Well, the upper bound test says if you take a positive number in the box, in other words, pretend you're dividing by x minus 4, so you put a positive 4 in the box, and you do synthetic division, and you end up with all positives or zeros in your bottom row of the synthetic division process, then this number right here has to be an upper bound for your zeros. There will be no positive zeros to the right of that number.
So if it's negative, it's not if any of those numbers are negative, there's not going to be a,
If this number is positive, it will be an upper bound as long as these are all positive or 0. If any of these are negatives, then this number is not a negative bound, and we tested that with that last example where, we tried 3 and we saw a bunch of negatives in there, and that guaranteed that 3 was not an upper bound. Okay, so now you graphed it, and who do I have as live presenter right now? Lily, is that you? Okay, so it looks like it's crossing where? -5. So go ahead and test this for us. We're going to just do a little test here, but this is not what you could do on a test or a quiz for me. Go ahead and menu. Okay, you're fine that way. That's fine. And you found a 0 at -5, 0. Okay, so I would want you to verify that by putting -5 in the box and doing synthetic division. What was this? 1, 9, 27, 35. Is that right? Okay, I bring down the 1. I multiply. That's -5. I add. I get 4. Multiply. I get -20. Add. I get 7. Multiply. I get -35. Add. I get 0. So it does work. And you would have to show this. And not only would you want to show this, just good. Ms. Tessick knows I'm not just cheating and looking at the calculator without doing any other work. You also need to do this to help find the remaining zeros. How does doing the synthetic division process help you find the remaining zeros? Matthew?
X plus 5 is a factor of x
So negative 5 works in the box, so you're saying x plus 5 is a factor,
Yes.
and then what?
Can you negative times x rewrite it as x plus 5 times x squared plus 4x plus 7.
Okay, this is to the first, this is to the 0. So we need what, x squared plus 4x plus 7. Everybody agree? Okay, you can try and factor this, but since we're not finding any more rational zeros, I don't think this is going to be factorable. Does that make sense? So I think we're going to have to do quadratic formula. Go ahead and do that, please. You do a quadratic formula on this to find our 2 remaining zeros. Now, we only saw it crossing the graph one spot, right? So I'm predicting that they're going to be imaginary, unless maybe we didn't zoom out far enough. But we know it's not going to be to the right because we were guaranteed with Descartes' rule of signs that there would be no positive real zeros. Oh, wow. Sorry, everybody. Maybe I should just turn my volume down there. Well, I don't want to turn down the recording, so, but I'm not sure if that affects it or not. Okay, let's see. Sorry about that. All right, so with quadratic formula, did you get something like negative 4 plus or minus square root of 4 squared minus 4 times 1 times 7 over 2, which would be negative 4 plus or minus 16 minus 28. Is that a negative 12? So it is imaginary. And let me just start my work on simplifying right now by putting this over 2 and this over 2. So I can reduce this now that I've split it up into 2 fractions. So I now have negative 2 plus or minus this. If I simplify that, isn't that square root of negative 1 times square root of 4 times square root of 3? So that's going to be I times 2 times square root of 3, which gives me a 2I rad 3 over this 2 here, right? And so this 2 can now divide out with this 2. I'm getting negative 2 plus or minus I rad 3 as the remaining 2 zeros. And they are imaginary. Are we okay with this? All right. Okay, so I think we did some good things on this problem. We did the rational zero test with the p's over q's. We did try a little bit of Descartes' rule of signs to determine how many positive or negative real zeros there were. And we also looked, I think, a little bit at an upper bound test, didn't we? We did an upper bound test? Okay. Questions on this? All right.
Is the upper bound test meant to cancel out any other bounds that could be? So when we did it with positive 4, that means that 5, 7, and 35 could have possibly been positive 4 plus the bound.
Positive 4 was an upper bound. That doesn't mean that 4 is going to be a 0. It just means that there will be no zeros to the right of 4.
Yes.
And we use that to eliminate the 5, the 7, and the 35 as possibilities.
So you can still consider anything past that an upper bound as well, right?
Oh yeah, yeah. If you tried 12, it's still going to work as an upper bound. If you try 100, that's going to be an upper bound also, right?
All right.
By upper bound, we just mean there's going to be no zeros to the right of that number.
That just got rid of 5, 7, and 35.
Right. I chose the number 4 to test so I could see whether I could eliminate 5, 7, and 35. Are we okay with this? All right. Let's see. Okay. All right, let's try this example here. Oh, you know what we didn't do? We didn't write it as a product of linear factors, did we? For this one. Isn't that the directions on the gift number 7? Okay, so what are, and I didn't even list our zeros. So what did we come up with for this? Is this the problem or no? Is it the same problem that we're working on?
Yeah.
Okay, so the zeros are what?
-5.
-5.
2 plus or minus I.
2 plus
IRAD.
IRAD 3
minus
and 2 minus IRAD. Do people agree? And then if we're going to rewrite our function so it's a product of linear factors, Matthew.
X plus 5 times the quantity of X plus minus the quantity of 2 plus I red 3 times the quantity of 2 minus 2,
We need X minus.
or X minus the quantity of 2
Yeah.
minus I
This
red
is because it gets -2, not 2.
For the.
Is it?
2 plus
Yeah.
I.
Right here?
Yeah.
Is it -2 plus IRAD 3? And thank you. So that should be a negative in there, that should be a negative in there. Okay, does this look okay? And of course, we would want to clean this up a little bit by distributing this negative here, this negative here. So this is going to be X plus 2 minus IRAD 3, and this would be X plus 2 plus IRAD 3, and multiply that by X plus 5. So if you multiply all of this out, you will end up getting, all the i's would drop out, and you'd be left getting, oops, not that one. This one. Does that make sense? Okay. All right. All right, anything else that I want to talk about in this section? Did I miss anything important? Oh, this is the one I was going to do, right? We didn't, I just remembered that we didn't finish up number 7, but I want to look at this one. It says, use the given 0 to find all the zeros of the function. So if 2i is going to be a 0, that's one of our, how many zeros are we looking for? 4, because it's a degree 4. This is only one of our 4 zeros. Everybody with me? Do you know any other zeros right away? Negative 2i, because the imaginary zeros, they come in complex conjugate pairs. So if a plus bi is a 0, then a minus bi is going to join it, all right, and it's going to also be a 0. So I know that 2i is a 0, so negative 2i is also a 0. So how is that going to help us find the other 2 zeros? So you want to write them as factors?
That's what you want to do.
I do. So if these are zeros, then what are our factors going to be? Or what would be 2 factors if we know 2 zeros?
X minus 2i and X plus 2i.
All right, so X minus 2i and X plus 2i. So if I multiply these out, or better yet, if you multiply these out, you're going to get a quadratic factor instead of 2 linear factors. And then I think we can make some progress in finding the other 2 zeros. When you multiply this out, what do you get? X. So this x squared, you got a plus 2ix and a minus 2ix, and what's this? Minus 4i squared. Is that right?
Yeah.
So these are subtracting off, and we end up getting x squared. This is a negative 1. So is this x squared plus 4? Do people agree? Okay. What are we going to do to find the other 2 zeros?
Factor out X squared plus 4.
Factor on x squared plus 4 from here.
Divide X x squared plus 4.
We gotta divide this into this, right? Or I could say, we gotta divide this by this. Can we use synthetic division? No. So go ahead and you get some practice for our quiz next class on doing some long division. We're gonna do x squared plus 4 into 2x to the 4th minus x cubed plus 7x squared minus 4x minus 4. Now I gotta say, my personal preference here, and you don't have to do this, I don't think, but I would, is add in any missing terms. You gotta add in a 0 for any missing terms here, but there weren't any, but I did have a missing term in my divisor, so I would fill in a plus 0x there. That's my personal preference. So go ahead and do that division. I'm going to pause this while you're dividing. It's not pause. Okay, let's see how we're doing with this. Did you say x squared times what gives me 2x to the 4th? What was your first term of your quotient? 2x squared. Did you multiply the 2x squared by each of these? Right? Okay, so that's going to be 2x squared times x squared is 2x to the 4th. 2x squared times 0x is 0x to the 3rd. 2x squared times 4 is 8x squared. And I'm going to subtract that, but I'm going to do that by changing it to addition and changing all these signs here. And when I add here, I get 0. When I add here, I get negative x cubed. When I add here, I get a negative x squared. Does that look right? And then I bring down the next term, which is a minus 4x. And when I do that, I can again say, what about this x squared? X squared times what gives me a negative x cubed? And that's going to be what? Negative x. So I want my next term to be negative 1x. I multiply by each of these three terms of the divisor. I get negative x cubed plus 0x squared minus 4x. And I subtract. I'm going to do that by adding the opposite. Change that to addition. Change all these signs here. I get 0. I get negative x squared. And I get 0. Does that look right? And I bring down my next term, and that's a minus 4, so I got a plus 0x and then minus 4. Does that look okay? You're checking me, quality control? And then I say x squared times what gives me a negative x squared? That would be negative 1. So I got to take negative 1 times all of that, so that is going to be negative 1, that's going to be negative x squared plus 0x minus 4. And now I'm going to subtract that, change that to, addition, change all of these signs here, and now when I add, I get 0, I get 0, I get 0. That's my remainder. Is this okay? How did that help us? Why did we even bother doing this long division process? So can we factor this function now? Can we factor our function any further? We knew that we had this quadratic factor, where was it? Here, right? Wasn't that a quadratic factor? Because that comes from multiplying this by this. So I have x squared plus 4, right, times what would get me back to my function? 2x squared minus x minus 1. How are we going to find the other zeros, Matthew?
Factor 2x squared.
You can try and factor this, see if that's factorable. If not, you do quadratic formula. Okay? Does it factor? Product is negative 2, sum is negative 1. Would that work? Negative 2 and a positive 1? I think it is factorable. Right? So you can go ahead and factor it. Go ahead and factor it. Does this look okay? Connected form? And then we set each of these equal to 0, and we get what? -1/2 and +1. Does this look okay? Go ahead and graph this function on your calculator and see if you agree that -1/2 and 1 would be the only real zeros for this degree 4, because it looks like we found 2 imaginary zeros, 2i and -2i, and maybe 2 real zeros, -1/2 and 1. Did you graph it? Let's see. Hope I not made presenter yet today. Matthew Armstrong. All right, so looks like you got a 0 at 1 and maybe 1 at -1/2. Can you confirm that by doing menu, analyze, 0? Gotta slide that over. The pressure, people watching you.
It's hard. Trying to slide it over. It's not. Slide it over on yours.
That looks good. No, okay, not too far. No, just over one. Just find one of them.
I got it.
So that's -0.5. Now you want to find the other one. So. Are we okay with this? It's working? You got 1 0 for that one? It's kind of overlapping the other. You could drag that out of the way so it's not overlapping anymore. Grab it. There you go. Slide it out of the way. Okay, now we can see both of them. Okay, so you would list for this problem the zeros are 2i, -2i, -0.5, and 1. Are we okay with this? I mean, you could do synthetic division to verify, but we already verified it algebraically, not just graphically, right, by factoring. Okay, so your task, I was going to start section 2.6, but with half our class gone, I will not. Instead, I'm going to task all of you with finishing this gift. So get together in groups, put yourselves together, and you're going to finish this gift up, and I will put your homework up.